Hello.
Hi, Laurent.
Hello, is that Tubagus?
Hi.
Hello.
So in there in the morning, right?
Yes, it's 9 a.m. Just the
9
right
a.m.
time.
Okay.
Just the right time.
Okay. So you are at home or in the campus?
I am at home. I am at home. Yeah, I stayed until the kids went to school and right in time to start my lecture.
Okay.
But now with the COVID situation, we can go, for now, we can go to the lab as much as we want now.
All right.
How's the situation regarding COVID in Indonesia? Do you go to work? Do you go to the office?
Yes. Yeah. We start go to the office like this month.
Okay.
Yeah. 3 days in a week. Yes. 75% working from working from the office.
I hope we will be able to meet soon.
Yeah.
Hopefully.
Yeah, I heard that will come to Indonesia next year, right?
Yeah.
Okay.
The date is not quite set yet, but maybe January. Maybe January.
Yeah, in January. Yeah.
Mm.
And he will be living in Indonesia for 1 year or 2 years.
Maybe 1 or 2 years. Yeah.
Okay.
I think he will have some choice, and he will be. It will be a postdoc, so he will be also applying for permanent positions at the same time. So in a way, it would be good if he doesn't stay for 2 years, because it would mean that he got a permanent position somewhere. But no, that's we were really happy, and both Gino and Dilruba, his wife, are so enthusiastic about going to live in Indonesia. It's
yeah, that's good. So what about you, Laurent?
I don't plan to live in Indonesia soon, but I would really like to visit Indonesia, probably in March, because Sonny Haribowo has to do some fieldwork. So he's been in France for 3 years now without returning back to Indonesia. Yeah. But now he has to do fieldwork, and hopefully we will go in March. We wait for the end of the rain season. He says that March would be okay to do field work in Java. Not too much rain, hopefully in March.
Yeah. So you will visit what is Sangiran, right?
No. It's mostly dedicated. It will mostly be dedicated to Sony's PhD thesis, and we will be doing some field work around Jakarta and Bogor, basically.
Okay, yeah, I see. It's about the fault, right? The fault that passed through the Jakarta and West Java, right?
Exactly.
Okay.
That maybe passes.
Maybe. I know. Okay, Bu Rima.
Yes, shall we start?
Ini lagi adzan, gimana?
Oh, di saya udah nggak adzan.
Oke.
Nggak apa-apa, sambil nunggu adzan aja, mangga.
Oke. Dimulai.
Sorry, can you just give me like 20 seconds, please? Sorry.
Yes, sure.
Okay.
I'm back. Sorry.
Oke, silakan Salsabila.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. I hope you are doing well. Welcome to the 4th student course about Geodynamic and Sea Level held by Oceanography study program. My name is Salsa, and I'll be your master of ceremony in this beautiful Friday. In this beautiful moment, I'd like to welcome Dr. Laurent Husson from ISTerre CRNS Université Grenoble-Alpes as our lecturer today, the Honorable Dr. Tarya as the head of Oceanography Study Program, Institut Teknologi Bandung, the Honorable Dr. Tubagus Solihuddin from the Marine Research Center, Ministry of Marine Affairs and Fisheries of the Republic of Indonesia as our moderator today, and of course, all of our beloved participants. In this special afternoon, we have several agendas, so allow me to read several sequences of our agenda. First, we have opening and student course rules, and then we will have opening speech by the head of Oceanography Study Program, Dr. Tarya, and we also have early photo session with Mr. Tarya in case Mr. Tarya has other important agenda to be attended. Then we have introduction of the speaker's profile by Dr. Tubagus Solihuddin. And then we have presentation session by the lecturer, Dr. Laurent Husson. And we have Q&A session guided by Dr. That we need to follow for today's student course. Allow me to read the rules. First, for participants, please change your display name to institution or university _ full name for the participants. And number two, during presentation, please participant must turn off the microphone and the camera can be turned on or off. It is optional. And the third, when turning on the camera, it is recommended to use the virtual background that has been provided, especially during a group photo session. It can be downloaded via the link that is on the screen. Then the fourth, for the Q&A session, participants are welcome to raise hands if you have questions. When the moderator has given the permission, participants can ask with the microphone turned on. And the fifth, the link of attendance list will be shared by the committee in the chat box by the end of the presentation. So without any further ado, let's step forward to the following agenda. That is opening speech from Dr. Tarya, the head of Oceanography Study Program, Institut Teknologi Bandung. To Dr. Tarya, the time is yours.
Okay, thank you, Salsa. Yeah, Assalamualaikum warahmatullahi wabarakatuh. And good afternoon, everyone. And thank you to everyone who joined us in this virtual guest lecture. Yeah, before we carry on to the virtual course, I would like to give my regards and appreciation to the committee who creates and organized this guest lecture series. And today is the fourth series in the frame of Nusantara program within Riset Kemitraan Dasar 2021. So I would like also say welcome to Dr. Laurent Husson from Grenoble University, France, as a guest lecturer today. And I would like to give you a short introduction on our department. Oceanography department, part of Faculty of Earth Science and Technology. Oceanography department has four main focus research: physical, biological, chemical, and geological oceanography. So the topic of this guest lecture today is geodynamic and sea level. Is very relevant with our focus research department and also with the academic activity. So without any further delay, I wish very nice guest lecture and warm discussion. So enjoy the event, everyone. And thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Ai, for the opening speech. As I mentioned before we move to the next agenda, let's take a photo session with Mr. Ai. So everyone, please turn on your camera and please use the virtual background that has been provided. And we'll give for like 5 seconds for everybody to be ready. Turn on the camera and use the virtual background.
We can't see your face, Laurent, so it's okay for you.
It seems that I have some trouble with the background.
Your face gone, Laurent.
Okay, is everyone ready? There are 2 slides, so we're gonna take for the first slide first. Okay, everybody, please be ready. We will take the photo in 1, 2, 3. Okay, and then we move on to the next slide. Everyone, please be ready. 1, 2, 3. Okay. Thank you for the photo session. The next agenda will be led by Dr. Tubagus Solihuddin. Mr. Tubagus is a researcher at the Marine Research Center, Ministry of Marine Affairs and Fisheries of the Republic of Indonesia. Mr. Tubagus will introduce Dr. Laurent and guide us until the Q&A session. To Mr. Tubagus, time is yours.
Okay, thank you, Salsa. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone, for those who are in Indonesia, and good morning, Laurent, from France.
Good morning.
Yeah. Okay, let me introduce myself. My name is Tubagus Solihuddin, and I will be your moderator in today's lecture. So first of all, I would like to thank to Pak Ayi, who has officially opened and given a brief note speech for today's lecture. Thank you, Pak Ayi. Okay. Secondly,
Welcome, Pak Tubagus.
Okay, thank you. Okay, secondly, thank you to our speaker, Mr. Laurent, for your availability to give a lecture today. Thank you, Laurent. And I would like to welcome to you all to this lecture, students, lecturers, and researchers. Thank you for your attendance and hope you enjoy this lecture. So before we start the lecture, please allow me to introduce our speaker, Mr. Laurent Husson. He is a research scientist from the ISTerre, Institut des Sciences de la Terre. In Indonesia, we call it Institut Ilmu Kebumian. So it's much similar with the oceanography. Yeah. And he's from University of Grenoble, France, and his research interests are in plate tectonics and mantle convection, dynamic topography, tectonic and orogenesis, current sea level, and vertical land motion, and also coastal geomorphology, coral reefs, and marine terraces. So he has conducted research related to his expertises in Indonesia, including in Java, in Seribu Islands, in Belitung, in Sumba, in Buton, Southeast Sulawesi, in Biak, Papua. That's all what I know, Roland.
That's correct.
Yes, you can add more if you like. And there is one interesting statement from your personal homepage. So you said that geophysicists call you geologists, and geologists call you geophysicists. So why does it happen? And how and how do you define yourself?
Oops.
Okay. Anyway, so I would like to invite Mr. Laurent to deliver your presentation. You have 1 hour for your presentation, Laurent, and after that we have a Q&A session. All right, Mr. Laurent, time is yours.
Okay. So shall I say share my screen? Yes. Okay. So I need to do this, I guess. Oops. Is that okay? Do you see my display correctly?
Yes, clear.
Okay, you have the full screen.
But you have your next slide on the screen.
So it's not the right one.
Yes.
It's always tricky to do this.
Probably.
I think if I do this, might be better. And now?
Perfect.
Yes.
Is that okay?
Yeah.
Okay. So thank you very much, Tarya. Thank you very much, Tubagus. Thank you, Salsa, for making all this happen. Thanks to the committee. It's exciting to be here with you. It's as Tubagus said, I've been many times to Indonesia, and Indonesia is very dear to my heart. So it's unfortunate that I couldn't go over the last couple of years. It's unfortunate that my Indonesian colleagues couldn't come to France either, but hopefully it will come back to normal, and we will be able to meet again and travel together and visit beautiful Indonesia and do nice work together. Hopefully we will go as I said, told Tubagus in March. Hopefully I will be able to visit you in Bandung, and we'll be happy to meet whoever is in the group here. So thanks very much for this introduction. Okay, so yes, I will talk about geodynamics and sea level. That's so needless to say that for Nusantara, for Indonesia, it's a primordial feature. The interaction between the solid earth and the sea level is actually the reason why Nusantara is called Nusantara. There's probably no other place on Earth that where the solid Earth and the hydrosphere share so many things. By the total coastline length of Indonesia, I don't know. I just coming out of my head, but it's probably the longest of any country, or maybe I don't know. It has the largest number of islands, I think. So yeah, needless to say that Nusantara is the right place to study the relationships between geodynamics and sea level. So because for geological reasons, as I suggested before, but also for other obvious reasons, which is the fact that it's critical to many instances. So because it for the services that it brings to Indonesia, like this is a fishing harbor in Indonesia, and I don't know which one. There's so many, so I don't know. Anyway, it's to mention that this is a good example of an interaction between the solid earth and the hydrosphere, because people go fishing. That's kind of obvious. Another example is the beauty of coral reefs that are, as you know, are really threatened currently, and they belong to they live exactly at the place where the solid earth and the sea interact. So they're critical also, and they are critically threatened, as you know. Last thing, another reason that might impose that we address the question of the relationships between the solid earth and sea level is the fact that a large part of Indonesia is vulnerable to sea level rise. You all know that Jakarta is dramatically threatened by flooding events, and it will probably get more and more harmful in the next future. So we need to understand what's going on. The reason why places like Jakarta are so much threatened by the sea level rise. But among those three aspects, I'm not going to talk about the instantaneous aspects of sea level, or not much about those aspects of sea level rise. For instance, like if Jakarta is getting flooded, it's not only because the sea is rising, but it's also because Jakarta is subsiding, and that's mostly for anthropogenic reasons, because we are pumping water underneath Jakarta. It causes subsidence in the region. But so I'm mostly going to talk about other processes that are most of them in the long term. Okay, so what is sea level, by the way? Either current or in the past. What is sea level? It's simply the intersection between the solid earth, that could be called the geosphere, geo being the earth, and the hydrosphere, the water. So that's what you see on that figure. So sea level is what you see here on this on this view, is the intersection between everything that goes inside the solid Earth and the sea level, the layer of sea on top of it. That might seem totally trivial, and it is in a way, but it opens when you think about it. We need to know what is the solid Earth. By the way, the solid Earth has a funny shape. This is the shape of the solid Earth. If you strip out the oceans, that's what you get with oceans with funky bathymetries. The topography is extremely rugged, and likewise in the continent. So this is the fact that it's so rugged is going that tells us that the Earth is not round. It's not a sphere, by the way. The geosphere is not a sphere. It's really rugged, and this is why it may interact with sea level. But the hydrosphere, the oceans themselves, are not a sphere either. The sea level is bumpy. This figure is the geoid. So that would be the shape of the Earth if it were totally covered by oceans. Is that okay? So that is the shape of the oceans. If we had no continents, that the oceans would be looking like this. Of course, there's a crazy vertical exaggeration to emphasize the bumps and the depressions at the surface of the oceans. Like this is south of India. So India is here, Indonesia is here. So that deflection here in south of India is the largest deflection, and it's only 150 meters or something like this. Likewise, in Papua, it's one of the highest here, and it's only about 100 meters. So the vertical exaggeration is enormous on that view. But if you think about it, plus or minus 100 meters is when you view it from the coastline, when you are on a beach. And you imagine that, say you're on the beach in Biak here, and you're looking at the ocean, and you imagine, well, then if the hydrosphere, the oceans were actually a sphere, the sea level would be 100 meters deeper than what it is today. So that totally modifies the interplay between totally modifies the location of the coastlines. So that figure that we all know, we are really familiar with that view of the Earth, is actually the interaction of two really complex structures. One is a solid Earth, and the other one is the hydrosphere. So that's another way to draw it. This cartoon is showing exactly what I just explained. If you the orange ellipsoid, the ellipsoid would be the geometry of the Earth if it was only a rotating homogeneous body rotating around its axis. It would have a shape of an ellipsoid, like the orange one. But it's distorted. And the surface of the Earth, as shown by the green curve, is distorted, and it has some bumps and holes that we call them continents and oceans, basically. And those depressions are filled up with the sea itself being bumpy. So we have the interaction of two bumpy structures. Okay, but the thing is that I say that the geosphere is not a sphere, but another important point about the geosphere is that its geometry, its shape changes through time. Likewise, the hydrosphere, the oceans, the hydrosphere is not a sphere. It has the shape of the geoid, and that shape also changes through time. The interaction between the two is going to change through time. Sea level is going to change through time. The mean sea level, but also the sea level the relative sea level that we can see at any coastline. It changes through time. What you see on this figure, it's the mean sea level, not change, but mean sea level over time over a long time scale. So we're talking million years, hundreds of million years, all the way to present day here. And those curves show the oscillations of the sea level over those long time scales. So we see that it may vary by several hundred of meters, the mean sea level over million years time scale. So that's over long time scales. As you can see, as you can remark, by the way, is that there's no clear consensus about the eustatic or mean sea level elevation through time. It's because the deeper you go into the past, the larger the uncertainty becomes. But it also evolves on short timescales. And here you have a similar view of this time we are talking about 1,000 years, so 300,000 years. So it's a late Quaternary, and we have sea level oscillating. So we are sitting here at present day, and the last time, not long ago, only 10,000 years ago, sea level, the mean sea level was probably 120 meters below its present day mean elevation. So the last time sea level was as high as today goes back to 125,000 years ago, during an episode that is called MIS5, for those who are familiar with this terminology. And we can also consider very short timescales, the historical timescales. So in that case, so this is we could extend this graph to 2020 now, but this one is a little old. But you can see the sea level is rising. It has been rising throughout the 20th century and continues to rise fairly quickly. So all those interaction, the reason why the sea level is changing at different timescales with different amplitudes is because we have many mechanisms interplaying together. The causes of sea level change are multiple. And this is what is summarized on this graph here. So you have time here in years. So it's a log scale. So we're talking about million years time scales and higher. And here we're talking about short time scale. The amplitudes also in a log scale, you see they vary quite importantly. And we have a bunch of mechanisms. And I propose to explore a few of them, one after the other. I hope it's not going to be too systematic and too boring, and you'll find the interest when thinking about, for instance, the relationship between Indonesia, between the solid earth and the ocean. If you think about it, then you might wonder, okay, well, when I go to my parents' place near the coastline of Sumatra, then I can see that this might be happening and so on. Okay. Let's start by the instantaneous timescales. That graph is comparable to the one that I just showed before. It's a mean sea level rise over the last 30 years. So you see that the sea level is rising by about 3 millimeters per year. And that sea level rise is obviously a big threat to many places, because in places like in Jakarta, for instance, it adds up to the subsidence, to the land subsidence. So it's not only the land is going down, but the sea is rising at the same time by about 3 millimeters per year. So that increases. This is actually what you see here. So this figure, I'm not so familiar with this graph, but I think it's coming from its mean sea level in Indonesia. It's been averaged to some extent, but I don't really know how it's been done. It's based on multiple spatial altimetry campaigns. So you see that it's oscillating quite a lot, but there's a trend of sea level rise by about almost 4 millimeters per year of sea level rise in Indonesia. So that's comparable to the mean total sea level rise at the surface of the Earth is slightly faster in Indonesia on average. Why is that? Why is it that the sea level is rising at present day on average? It's due to climate change, obviously, as you know. But the main cause is not the fact that there's more water in the ocean. It's because the temperature is increasing, so the density of the seawater changes. It expands, and so there's and then it causes the sea level to rise. So that's what I summarize here with those cartoons here. If there's a bucket filled up with water, we see that the mean elevation of the water in the bucket is increasing. That's mostly due to the thermal expansion of the water. That's if you have a bucket of cold water and a bucket of warm water with the same amount of water, the water table will not be at the same elevation. So if you warm up the water, you increase the elevation, and that is the main cause of the sea level, the fast sea level rise that we're experiencing at present day. The second cause of that sea level rise at present day is ice melting, where the ice that is stored at the polar caps and in some glaciers, including in Papua, are melting and adding some water into the oceans. It's not the water is not locked in the poles. Is no longer locked in the poles, but is melting and going into the oceans. That adds up. That also contributes to sea level rise, just because there's more water in the oceans. But that contribution is fairly small compared to the thermal expansion of the oceans. That's what I tried to explain with these two cartoons of showing the buckets. So that's for instantaneous timescales. I'm not going to talk about the local effects of like subsidence due to anthropogenic activity that also contributes to modify the sea level. Now I'm going to consider slightly longer timescales. It's one thing that is called post-glacial rebound. So that's also related to the ice melting, but this time I'm not talking about the current melting of the glaciers caused by anthropogenic activity, by humans' impact on the climate that causes the ice to melt. I'm talking about the glacial cycle that time. So basically, if there's an ice mass somewhere at the surface of the Earth. So typically, it's I'm talking about the polar caps here, the ice that is stored in Antarctica and Arctic Ocean, and because it's because of the mass is loading the surface of the Earth. It's causing the solid earth to respond. So the mantle, the solid earth itself is flowing to accommodate this extra load, because the solid earth is not solid on this timescale. It has some viscosity and it can flow. The rocks themselves are flowing, and it causes there's an interaction. So if the ice of the polar caps is melting and building up again, melting, building up again, melting, building up again, this is the glacial cycle, glacial interglacial cycle, better say. It's going to change the response of the solid earth. So of course, if we load the surface of the Earth with a mass of ice, there will be a deflection. The mantle will flow next to it, but next at larger distance, you have also a response, even where there's no ice. So on this cartoon, you can see that on the edges of the polar caps, we see the Earth is rising here. So we have uplift here, subsidence here, and conversely, when the the ice is melting, the surface is rebounding and where the ice used to be, and we have a collapse of the edges. So that simple cartoon explains the mechanisms at play, but you can don't think that this is only restricted to local. It's not located only. This effect is not restricted to the polar caps. It's acting at large distances, and it operates on different timescales. So this is a little bit the same, comparable. This is a comparable cartoon, but except that we divided the timescales into two timescales. One is the elastic timescale. So elastic means that there's no time dependency in the response, because the solid Earth has a multiple behavior. Part of it is elastic, part of it is viscous. So because of that, we have two timescales of response to ice melting. The elastic component of it responds instantaneously to the unloading of the ice. And on a longer time scale, you see the mantle flowing underneath it. And this is a viscous flow, meaning that there's a time dependency on that flow. So you can unload, but then it takes time before the response fully operates. So this is important, because that means that there's a part of the response to ice melting is instantaneous. That's one thing that is easy to understand, but also that the melting of the ice that occurred 10,000 years ago, for instance, when the ice cap started melting, we are still seeing the response of that ice melting. So this is operating mostly, obviously, at where the ice used to be. Typically, it's where the red parts are. So it's in Antarctica and in Fennoscandia or in North America, there used to be ice caps covering those areas, and those areas are going fast upwards at really fast rates. We're talking about up to 10 millimeters per year. So this is really, really fast, up to 18 millimeters per year, if I trust this figure. But you can also see that the response is also taking place at large distances from where the ice used to be in North America. So you see the uplift of the northern part of North America, but the rest of it is subsiding here. This figure doesn't show doesn't give enough details to show the response at larger distances, but in Indonesia this is happening too. So there's a good record of this process in the field. For instance, those are raised beaches in Scandinavia. So from here, I'm not exactly sure where this photograph is taken, but what you can see here is sand beaches that are being more and more that are being uplifted. So this one is the oldest one. This one is the active one. So because the land is rising due to post-glacial rebound, we see a sequence of beaches that are being raised. So that's quite dramatic. Here we're talking about many tens of meters. So that's really important. Now, in the far field, like in Indonesia, we also see the impact of post-glacial rebound. Because the ice is melting at high latitudes, it changes the global shape of the Earth and the global shape of the oceans at the same time. And this is why, for instance, if you go to Belitung or to Sumatra, you see those kind of things that are micro atolls. So those are coral structures that normally grow at shallow depth in the oceans, like maybe here. Those ones might be alive, but because there are really good markers of sea level, because they live really close to sea level. And of course, you can guess that if you find two things covered with grass, they are dead and they're just above sea level. Maybe maybe a meter or two above sea level. And that's because that's the effect of post-glacial rebound. It has modified the coastline of Indonesia, and we know this because we have fossil microatolls that are not very old. Those ones are late, are Holocene. I think they're dated like 6,000 years ago. So they're not very old, but it tells you that the landscape has changed due to post-glacial rebound. Yeah, so that's okay. So this effect, when I was showing the microatolls of Indonesia, I was referring to the very last stage of glacial melting. So this is time is going this way on that figure. Present day is on the left-hand side, and sea level is the changes in sea level. You can see that it's been oscillating through time, and that is accompanied by post-glacial rebound at each time. So we go from glacial to interglacial to glacial to interglacial. And we've been doing this all over the Pleistocene with different amplitudes. The amplitude is increasing as we're going towards present day. And the frequency also is changing through time. But in any case, all these oscillations are accompanied by some ice melting and build up, ice melting, build up. And this is going to change, to have some post-glacial rebound at all the cycles. All right, so now let's move to much longer timescales. One of the main control of sea level is called tectono-eustatism. So that's eustacy related to plate tectonics, basically. So if I take the morphology of the oceanic basins here, we can see that they have variable bathymetries. We can see that there are some mid-oceanic ridges, like here in the Atlantic. You see in white, it's shallower. The oceanic ridges are shallow. You can see them in the Indian Ocean. You can see this one going underneath between Australia and Antarctica, going all the way to North America. Those are the mid-oceanic ridges take some space into the oceans, and that space is not available to seawater. So depending on the geometry of those ridges, of those mid-oceanic ridges, depending on the volume they occupy in the ocean, the sea level might be higher or lower. So this, if I make a cross-section, for instance, across the Atlantic, for instance, like an idealized cross-section, cartoonish cross-section here. So I have South America here, Africa here, and in between there is the Atlantic Ocean with an oceanic lithosphere with a ridge that doesn't go all the way to the surface, but not unlike what I should draw in this cartoon. But the bathymetry increases away from the ridges towards the edges on both sides. And the volume of the ocean is therefore defined by the geometry of the oceanic lithosphere. And yeah, if you compare that view of the bathymetry of the ocean, and here with a view of the thermal age of the oceanic basins, I'm not exactly sure how all of you are familiar with the plate tectonics of oceanic basins, because I think that many students here are mostly doing oceanography and maybe not on the physical oceanography. So in any case, I'm sorry if that's too simple for many of you. The oceans are spreading at mid-oceanic ridges. That means that here it's where the mid-oceanic, the ridge is active. We have volcanoes here, and there's a spreading away from the ridges. So that means that, for instance, in this cartoon, this place is older than this place, which is older than this place, and the youngest place being here. So the further away you go from the ridge, the older the the oceanic lithosphere is. So that means that there's a good correlation between the bathymetry, the depth of the ocean at any place, and the thermal age, the age of the of oceanic basin, the age at the time at which any piece of the lithosphere was formed. So there's a good match between the two. We know this and we understand this. It's because it's cooling. It's the lithosphere, which is being formed at mid-oceanic ridges, is cooling as it goes away from the ridge. And when it's cooling, it's getting colder, obviously, and therefore denser, thicker and denser. This is what you can see on this cartoon too. It's getting thicker, but it's also getting denser, and then therefore it's getting deeper. And that is going to control the geometry of the oceanic reservoirs. So yeah, this is also what those are the data actually that you can see. This is the bathymetry of the Earth as a function of the thermal age, the age of the oceanic lithosphere. So of course it's really noisy, but overall you see this trend, which gives the mean profile of the lithosphere as a function of age. You can see that it's the shallower, the youngest, the shallowest the lithosphere is. And this is also true for the thermal structure. You can see that the young structure are extremely hot, and as you go away, so that's heat flux here as a function of thermal age. So the oldest pieces of the lithosphere, which are currently 180 million years, the heat flux in this area is less than any youngest place on Earth. Now that is going to do, I'm going back to my bucket because the oceans might be considered as simply as buckets filled up with water. The oceans are reservoirs of seawater. And the oceanic lithosphere defines the volume of the oceanic reservoir. And what's important is that that geometry of the ocean was not the same throughout the history of the Earth. Sometimes the oceans were narrow and young, having a young mean thermal age. Sometimes we've had old and wide oceans, and that is going to control the morphology of the reservoirs. Right? That's what I drew on this cartoon. So here we have an old ocean, which is the mean thermal age is large. It's an old ocean on average, and therefore the bathymetry is on average large. Therefore, the sea level is low. For the same amount of water, the sea level is lower than in that case where we have young oceanic basins. The mean thermal age is young. Therefore, the mean bathymetry is shallow, and therefore the bucket is smaller. And and you might expect to have some floodings during this period. So that's tectonostudism is actually one of the main processes that we can think of to explain the long-term variations in sea level. This is what you see here is a simplified drawing of the thermal age of the Earth through time. So this is present day here, and now you have 65 million years and 140 million years. You can see that the thermal age is much different during all those periods of time, and that is causing a different distribution of the thermal age through time. So for all those periods, you can see for this period at present day, we have this distribution of seafloor age, going all the way to 180 million years. But at 65 million years, we didn't have any old ocean, and the situation was even different 140 million years ago. So this is going to cause amplitude variations in sea level. This is going to cause the sea level to vary by plus or minus 100 meters within geological timescales. That's probably the cause the main cause of the eustatic changes that we see on the long term. Okay, now there's a few other mechanisms that I want to discuss here. Keep in mind that tectonoeustatism is probably the main one, but we can also think about different ones. One is orogenesis. So this is this figure shows the morphology of the Earth at present day, and we see that we have mountain belts. We have many of them. We have in North America, in South America. Obviously Himalaya and Tibet, and the Alps here that we barely see, but we have many mountain belts at present day. Now, if you think about the distribution between land and sea is defined by the space that continents are going to occupy at the surface of the Earth. So if we have large continents, then they're going to occupy more space over the ocean. The surface ratio between land and ocean will be defined by will be modulated by the dimensions of the continents. Now think about mountain belts as a shrink piece of continent. In order to have mountain belts, you need to shrink the continent to increase its crustal thickness. So that means that, for instance, here in Tibet, for instance, the crust is probably twice as thick. So that means that we have shortened this distance used to be twice longer before the collision of India into Eurasia. That's as much space that has been given back to the ocean because India is advancing towards Eurasia and leaving some space for the ocean. So if you this is the current situation, but it hasn't been the case at all times. So time again, we go from 140 million years all the way to present day. These are showing the continental drift at the surface of the Earth. So we go from almost Pangea stage to the present day configuration. And what is important, maybe we don't look at all the way back to 140, but maybe simply to see at 60 million years. What we see on that map is that we have very few mountain belts. India has not collided yet with Eurasia, so Tibet is not here, for instance. The Andes are much smaller. The the North American Cordillera is much smaller. That means that the continents were, on average, most of them were wider than what they are today. So the surface occupied by the continents is used to be larger. So that's what I represented in this cartoon again here. So at present day we have many mountain belts. That means that we have more space for the oceans. And therefore, the oceanic reservoirs are wider than what they are at present day. So it implies that the sea level could have been higher in the past because we had less mountain belts. We evaluate that this contribution could be up to 30 meters of sea level change. A fairly similar mechanism is the role of sediments in the oceans. Think about the ocean. The oceans as a big bucket filled up with seawater. If on top of that you add sediments on top of seawater, then of course the sediments are going to occupy some space in the bucket. The more sediment, the quicker the bucket will overflow, or the water level in the bucket will increase if you add some more material in it. So that map shows the total sediment thickness at present day, and you can see that it's not negligible at all. The total amount of sediments is pretty high. We have several places where it's in excess of 10 kilometers of sediments. Most of the time, it's not that much. But still, there's a lot of sediment in the oceans at present day, and of course, it might have changed through time. The total amount of sediments might have changed through time. This is again going to cause a modification of shape of, it's going to modify the shape of the oceanic reservoir. This is what I show on this cartoon here. If I add some sediments here, mostly coming from the continent, it's going to take some space, some volume into the oceanic reservoirs and cause the oceans to go up. This mechanism is somewhat comparable to the effect of mountain belts, and we anticipate that it might account for plus or minus 30 meters of sea level change through time. Another mechanism that operates on the geological timescale, the long time scale, is a geoid. So I commented on that figure during the introduction, and I say that in Papua we have a geoid high at present day, we have a geoid low in India at present day, but this figure has been changing through time. The reason why we have those bulges of the geoid is due to the distribution of the masses inside the Earth. So this is a cartoonish cross section of the Earth. This is the core, this is the mantle, and this is an ocean without continents. I didn't put any continents. So we have a layer of ocean on top of an idealized Earth. But inside the Earth's mantle, I put some mass anomalies. So the blue one would be a denser unit, denser than the surrounding. The red one would be a lighter one. Oh, sorry. Yes, that would be a lighter one. So because of gravity, simply because of gravity, this mass excess is going to attract anything around it, including the hydrosphere. The oceans will be attracted by this mass anomaly here because it's that's gravity. So and this is going to cause a bulge of sea level here. Instead, here, if you have something that has a low density, lower than average, then the seawater won't be as much attracted towards by that piece of mantle, and that causes a hole, a deflection in the geoid, in the sea level, in the water table. So that if you of course, this is not the real structure of the Earth, but the structure of the mantle is very heterogeneous. We have subducting plates into the mantle, the lithosphere is subducting into the mantle, and we have plumes, hot plumes rising into the mantle, and those are mass anomalies into the mantle. And those mass anomalies are going to attract or repulse the sea level, the seawater. So that's the explanation for the structure. For instance, here in Indonesia, the reason why we have a geoid like this is because we have many subduction zones here. Many plates, many oceanic lithospheres have been subducting underneath Papua and Indonesia. And that causes mass anomaly, positive mass anomaly into the mantle. The mantle underneath this region is extremely dense, and it attracts more water, and that water piles up at the surface of the Earth by about 100 meters. That's the geoid, and that geoid makes the sea level higher in Indonesia than elsewhere, for instance. And of course, that geoid is going to change through time because it's, as I said, it's mostly due to the internal structure of the mantle. And I mentioned the subducting oceanic lithospheres that are dense, subducting into the mantle. And so, of course, this is going to, then the geoid is a response to this structure, is a response to the tectonic history of the Earth, meaning that depending on where the subductions used to be, depending where the rising hot plumes in the mantle used to be, the geoid was different at different times, geological times. No, of course, it's going to, we can complexify the situation to see its impact on sea level. No, I put some continents on that structure, on that theoretical Earth, we have some continents here that are, this one is placed where there's nothing special above it. And in that case, I put one above the low mass anomaly. So that means that it's hiding the depression. So that means that it's hiding this piece of the geoid. Then the sea level, then the sea, the sea, it doesn't have much of an impact. But conversely, if the continent is here, where there's a geoid high, then it's going to shield all this piece of water won't be able to be stored above that mass anomaly. It has to be spread elsewhere in the ocean. So it's going to that volume of seawater in that case will have to be distributed in the oceans elsewhere. And those oscillations, depending on the location of the continents, then it might or might not shield the geoid bulges and deflection, and therefore modulate the sea level. So I'm going to talk about a concept that I've been working on for several years, and it's one of my main toy, so to say, is dynamic topography. It's related to the geoid. So we start with the same kind of idealized structure. We have mass anomalies in the Earth that are causing the geoid. So we have bumps and deflections in the geoid. But because, if you remember, I said that the Earth's mantle is viscous and is deforming through time. That means that, for instance, if this is lighter than elsewhere, it will probably go up into the mantle. If this dot here is denser, it might go downwards. And this is going to cause a flow and distort the surface, not in that case, not of the oceans, but it's going to distort the surface of the solid Earth, or the viscous Earth, better say. So, and importantly, then you can see that on top of that dense anomaly that is going down into the mantle, then I have the surface has a deflection here. That means that sea level, the seawater will fill that deflection. Conversely, if there's a hot low density body in the mantle that is rising towards the surface, it may cause a bulge, and then there's no more space to store sea level here. That could be a subducting plate, and then I expect to have this. I expect to have the surface of the Earth to be deflected above the dense mass anomalies. I expect the surface of the Earth to be deflected above subduction zones in particular. And there's one place on Earth that has many subduction zones, many slabs into the mantle. That's Indonesia. We have many subducting lithosphere underneath Indonesia. So we're very much into this kind of situation in Indonesia. I'll come back to this very soon. Oops, yes. So so that was a cartoonish view. This is a result of a numerical simulation. So what we did here is we accounted for the location of the mass anomalies into the mantle. I could explain how we did this. We use seismic tomography to determine the density field into the Earth. We compute the flow, the viscous flow, and then we are capable of computing the vertical traction underneath the lithosphere. So what we come up as a result here, so Indonesia is here, India is here, Africa is here, South America is here. So basically we see, that's what we call dynamic topography. The scale is in kilometers. So we have up to 100 meters to kilometer scale deflection of the surface of the Earth, of the solid Earth. And what we can see is we see a fairly simple structure. We have two red patches, one in the Pacific, one in the Atlantic, and we have two blue patches, one in South America and one focused in Southeast Asia. The main one is in Indonesia. The heart of that deflection is in Indonesia. So that's because we have many, we have the Pacific subducting plate, we have the Indo-Australian subducting plate underneath Indonesia. So they're all going down into the mantle, subducting into the mantle. And by doing so, they're pulling the surface downward and cause a deflection of the surface of Southeast Asia. And that makes a reservoir of seawater that allows the water to cover part of Nusantara, basically. All that place, all the west of Indonesia is a continental plate that is partly flooded. The Java Sea is really shallow. It's only it's less than 100 meters. But if it's a sea and not a continent, it's because it's being pulled downwards by the subducting plate. If there was no dynamic topography, the Sunda shelf would be continent, and you could go walking from Java to Kalimantan. Okay, so that was I talked about different mechanisms. I hope that was not too tedious, but now we will move to a case study focusing on one particular aspect, which is dynamic topography as a modulator of sea level in Indonesia. So yeah, the Indonesian case study. Obviously you all know this map better than I do, but I want to highlight the fact that so this piece of continent, the Sunda Shelf, is a continent, but as you know, it's flooded. There's a shallow sea between Sumatra and Kalimantan, and Java and Kalimantan. There's a shallow sea here. This is very shallow, but it's also gigantic. Huh? We're talking about several thousands of kilometers. Likewise, in North Australia, we see a piece of continent that is being flooded here. And this is because, in both cases, this is because we're getting very close to subduction zones. Those are the trenches showing the plate boundaries between Indonesia or Southeast Asia and the Indo-Australian plate. You have the Pacific plate here, and they're subducting underneath Southeast Asia on all sides. So we have many subduction zones that are pulling the surface of those continents downwards, making them flood. Okay, so we have observations for this that tells us the behavior. If we look at the coastlines of Indonesia, there's a striking distribution. Everything that in Wallacea or everything in East Indonesia is covered by, we see uplifted fossil reefs everywhere. Like here, this is in Southeast Sulawesi, in Buton Island. You see the structure here. You see those terraces. Those are all coral reefs that have been uplifted to several hundred meters. And you can see everywhere where you see red dots, that means that you have uplifted fossil reefs. That comes from the geological map of Indonesia. Conversely, if you go to Sunderland, you see mangroves and alluvial plains everywhere, and mangroves, and you never ever see any uplifted coral reef. So that's just looking at, and this is also true in Sahur, in North Australia. This is already suggesting that Wallacea is uplifting. There's pretty much no doubt about it because we see uplifted fossil reefs. And in Sahur we see, and in Sunderland we see no uplift. We see no evidence of uplift. We see alluvial plains and mangroves, which are better indicators of subsidence more than uplift. We have more information in Sunderland. There's this very relevant article by Solihuddin from the Java Sea, where he presented some shallow seismic lines across the Java Sea, and we see several layers of Pleistocene sediments being inside. So we see river incisions now and then, and we have, so that means that we have several during the Pleistocene. We have had a few episodes of regression and transgression with during episodes of transgression, we have deposition of sand onto the shelf, and during regression, the sea level was lower, and we have rivers incising the freshly deposited sediments. And we can count the number of episodes of flooding, and use that as an indicator of the rate of subsidence. Say we have about 5 episodes of at different places on average. We have about less than 5 episodes of transgression with sediments being deposited. That means that's sea level through time. That means that the continent has been subsiding recently to meet sea level only 5 times. If it was not subsiding, it will have met sea levels many more times. The first time it hit the sea level was met by the Java Sea was 4,000 years ago. Before that, all this part was a continent. You could go not so long ago, at any time before 400,000 years ago, you could go walking from Java to Kalimantan. That's because this region is subsiding, not at a crazy rate, about 0.2 to 0.3 millimeter per year. We can make observations of that kind also using coral reefs. Tubagus is an expert on that. He did very similar work in North Australia, and by studying the geometry of the active and fossil coral reefs and the distribution of mangrove at present day. I'm not going to go into the details, but if you study this kind of landscape where you have the mangrove on the back, a flat coral reef being presently occupied by the mangrove, and the propagation of the coral reefs and so on, you can deduce the rate at which the coral reefs are subsiding. And likewise, it goes very well with what we found from the shallow seismic sections from Solihuddin. We see that it indicates a subsidence of about 0.2 to 0.3 millimeter per year for the Sunda shelf. So not only Sunderland is subsiding at present day, but it's been subsiding for quite before that. And we with Sonia Ribo, we had access to thanks to Pusdatin. This seismic line is courtesy of Pusdatin. We've had access to many seismic lines for Sony's PhD thesis. And what we see here is that seismic line here. So it's 2 seismic lines actually, that with a gap in between. What we see here is that we have a tilt of the Miocene platform is being tilted, and we have the Plioquaternaris layers that are being deposited above it. So there was a tilt long ago, during sometimes prior to Miocene probably, and it's the shelf is dipping. The basement of the shelf is dipping by about 0.6%. So it's not much, but it's enough to determine the structure, the sedimentary structure on top of it. Okay, so I'm not going to go to explore Sahul here. Again, those arrows belong to Tubagus, several of them, I think. Showing subsidence in Sahul, and we also have uplift in Wallacea, and we have subsidence in Sunderland. So I will focus now on Sunderland, which is tilted southward. We know that we can measure it from the seismic lines, but it's also subsiding at present day. And now I'm going to go into geodynamics, and I will try to be as simple and quick as possible because I see that time is flying. The main event that occurred in Indonesia is the collision of the Australian continent with Southeast Asia. So this is from 15 million years to present day. The red Australian continent has been colliding, and it has changed the subduction dynamics. I'm going to be quick on this because it would take a long time to explain, but basically this is a subduction. The subduction here, and in brown here is kind of the Australian continent, because the Australian continent doesn't want to go into the subduction zone. It's going to disrupt the subduction of the Indo-Australian plate, the flow will be different. We tested this with a numerical model that is shown here. So you recognize Sunderland as a continent here. That's why you don't see really Java or Kalimantan. You see Sunderland as a continent. Likewise, you have Australia as a continent, and you have a few islands. That's the setup of the numerical models that we did. And we have subduction all the way here. Now I'm going to show you this movie that shows the result of the numerical model. So what you see here is Australia, the Australian continent sitting on an oceanic lithosphere that is subducting underneath Indonesia. And what you see here is some sort of Sulawesi, and what you see here is some sort of Sunderland. Now, what I want you to look at is the topography of Sunderland during the evolution of the subduction. Subduction proceeds. And look at here what's going on here. We have subsidence here. Because of the subducting plate here, we have subsidence, and we have Java here, Java Island, and Kalimantan, and in between we have a basin. This basin is due to the evolution of the subduction, and likewise in North Australia you have some tectonic activity and subsidence in the north of Australia taking place. I'm not going to go into the details because it would require a lot of time to explain many geodynamic concepts, but those are snapshots in case the movie was not really good quality. The evolution through time, we go from here to present day, that could be here. So just have a look at Sunderland here. Because of the subduction underneath, it's getting tilted toward the trench. That's why you go from brown to green. Sunderland is being tilted, and that tilt increases all the way to present day. So that really conforms to what we see at present day. We see subsidence, so all the blue triangles are showing subsidence, and we see that the plate is being tilted. We've seen that from the seismic line. So those are the model predictions those are the observations, and those are the model prediction that the deflection of the plate of the shelf above the Indian subduction. Okay, so I just want to emphasize that dynamic topography is responsible for the long-term tilting and flooding of Sunderland. This is on geological timescales, on long timescales, and also because of the effect of Australia, of the continent. The Australian continent enters the subduction. It modifies the mantle flow and causes subsidence as we measure it today in Sunderland or in North Australia. And so, yeah, I'm going to finish here. If there's something to remember from a theoretical point, is maybe you want to remember that geodynamics, in the sense that the deformation of the solid earth during geological timescale is a prime control on sea level. That geodynamics has actually multiple processes. There's no single process. We've been talking about the geoid, we've been talking about dynamic topography, we've been talking about tectonostatism, and so on. And those multiple processes operate at multiple time scale and space scales. In the case of Southeast Asia, Nusantara in particular, of course, geodynamics modifies the sea level. This is true at long time scales. We've just seen the example of dynamic topography on long time scales, but also at very short time scales. And of course, Nusantara is critically exposed to sea level changes at all time scales, but you knew this already. Thanks very much for your attention. I'm going to stop here, and I would be happy to answer questions if there's any. I hope I was not too long.
Okay, thank you, Laurent. Just in time. So now we are in 4:20, and we have 30 minutes for the question and answer session. Thank you very much for your informative and interesting talk, Laurent. yep, hope the student mostly because I think the audience is student, so hope they didn't have any difficulties to understand your presentation. It's because there are so many terminologies that probably they are not familiar with. So yeah, it's okay. But before we go to the question and answer session, so I would like to highlight some important points from your presentation. First, the cause of first, the sea level. The first point, the important, the first point, the sea level is always being changed through time, right? So both in multiple time scale and amplitudes. And the second, the cause of the sea level change categorized as three, as you mentioned. First, instantaneous time scale, such as thermal effects, and second, short time scale, like post-glacier rebound, that contribute up to 120 meter amplitude of the sea level, right? So you mentioned the sea level change from the LGM, last glacial maximum, like 20 million years ago. So and up until Holocene, like the sea level rise up to 120 meter, and the geological time scale. Okay, this is the longest time scale, like tectonoeustasism, orogenesis. Ini orogenesis itu adalah ini ya. Sorry, I talk in Indonesia, Laurent. Orogenesis. Ya, oke. Ya, orogenesis itu earth crust deformasi ya, deformasi permukaan bumi. Kalau apa? Ini because this is the terminology, geological terminology, so I have to explain. Okay.
No, yes, please explain me. Help me with this. Yeah, I cannot do it in Bahasa.
Okay,
so please go ahead.
Yep. Okay. And then the sediment cover also categorized as the geological time scale, that cause of sea level change, and geoid, and also dynamic topography. And the third one, you also did some studies in Indonesia, as you mentioned in your presentation, in Belitung, which represent Sunda Self. You said that in Belitung or Sunda Self indicate subsidence at rates 0.2 to 0.3 millimeter per year. So, and also you mentioned you categorize or you classified Indonesian archipelago into three area. Sunda Self represent Western Indonesia, and Wallace represent Central Indonesia, and Sahul Self represent Eastern Indonesia. Okay, so now we come to the question and answer session. Please, if there are any question from the audience, please raise your hand and mention your institution. And I think Laurent will answer straight away. Okay. Okay. Okay, please, if you have any question. Okay, I see there are two students raise hand. Okay, first I give the opportunity to Nadira de la Vida. Okay, Nadira, if you want to address the question straight away to Laurent, please.
Okay. First and foremost, I would like to thank you to everyone that held this lecture, and to Mr. Husson. I highly appreciate your lecture and those simplification that allows us to understand this lecture easily, and your illustration is quite interesting. So my question is, why is the ice melting percentage to sea level changes is smaller compared to the thermal expansion?
that's short answer would be that's, thanks for your question. Maybe yeah, I didn't give any explanation. The short answer is that's because that's what it is. That's what physics tell us. So those processes are unrelated, I would say. If there was no ice melting, because the climate is warming up and the oceans are warming up. We know this. We know that in Indonesia, for instance, the temperature of the sea is increasing. So the uppermost layer of the ocean is warming up, and that's the density of the water changes with temperature, and for only a few even less than 1 degree of temperature change causes an important dilatation of the water. But the reason why it gets so important on average is that it's also because there's an enormous volume of water. So if even if the thermal expansion is quite small by its absolute value, but because there's so much water, even a small thermal expansion of a gigantic volume of water causes some expansion, so an important expansion. Now the other process, which is the adding more water from the converting ice into water, that's because that's only what it is. The volume of water it is important, but it's not causing. It's the increase of the sea level rise due to ice melting is not going at the same rate as the thermal expansion of the ocean. But don't get me wrong. Don't get me wrong. I'm not saying that ice melting is not important. If Greenland, if the ice cap of Greenland or the ice cap of Antarctica is totally melting, which is a possibility, it will contribute to sea level rise by a crazy amount. For now, it hasn't. Those ice caps have not entered the super fast melting rate that is expected to happen very soon. It will happen in a few years from now. The acceleration of the melting of Greenland might have started over the last few years. It will increase through time, and in that case, it's very possible that the contribution of adding more water into the ocean will be more important than the thermal expansion of the ocean. So at present day, this is what we understand, that the thermal expansion is more important than the fact that we are changing ice into water. But in the next future, it might well reverse, and sea level rise will accelerate due to the melting of Greenland and Antarctica ice caps. I hope that that answers your question.
Okay, Nadira, does that answer your question, or you want to ask more, probably?
No, it's enough. Thank you for your answer. Merci beaucoup.
Okay.
Merci, Nadira.
Thank you. Okay, we go to the second question. I give the opportunity to Nabila. Please, Nabila.
Okay, can you hear my voice clearly?
Yes.
Okay. First of all, thank you to Tubagus for giving the opportunity, and thank you to Laurent for giving this explanation about the geodynamics and sea level. First of all, my name is Bella, and I'm gonna ask about two questions, I guess. The first one is, from what I know is that there's a lot of factors that affect from this sea level rise, such as the thermal expansion or tides and many more. I'm curious about actually, which is the major factor that affects the sea level rise, especially in Indonesia? Is it the thermal expansion, or is it about the tides, or maybe there's another factor that brings the biggest effects in the sea level rise in Indonesia? That's the first question. And the second one is, I'm kind of curious about the sea level rise, which country that gets the biggest effect from this sea level rise, actually. Maybe there's a lot of factors that cause the sea level rise. So maybe there's some country that will get the bigger effect from the sea level rise. So did you get my question?
Yes, I did. So
yeah.
First question is the most important mechanisms in the case of Indonesia. So actually, that's a very good question. I didn't talk about in order to be simple. I didn't mention the difference between absolute sea level change and relative sea level change. So absolute sea level change is kind of the uniform sea level rise that is on average at the surface of the Earth. So, for example, if you add more water into the oceanic reservoirs, it's a uniform process because the water is distributed at the surface of the Earth. So that's a uniform thing. That's sometimes called eustasy, also called absolute sea level rise or geocentric sea level rise. So that's a few things. But if you want to consider a specific place, you want to basically what you want to do is you want to consider relative sea level rise. That means that you're standing on the coastline of Indonesia, and you're looking at how the sea level is going to change at that location. And then there's different contribution. One is a contribution from the absolute sea level rise, but maybe the land is subsiding, maybe the land is uplifting for geodynamic causes. And those are local things. For instance, during the last part of my talk, I talked about dynamic subsidence in Sunderland. This is only a local thing. It only happens in Indonesia. It doesn't happen. It doesn't have a global impact. So then your question is actually what is the if I could reformulate your question, it would be what are the main causes of the relative sea level change in Indonesia? And then at present day, you're talking at present day, I assume. So in the case of Java, in particular, which is very flat, so it's extremely vulnerable to sea level rise. Jakarta, as we all know, is extremely exposed to sea level rise. Then I think the main control on that subsidence, the fact that sea level is rising at a fast rate in North Java, is due to anthropogenic causes. The fact that we are pumping water and hydrocarbons that is buried in the soil and bringing it up to the surface causes a subsidence at a really quick rate. In the Jakarta Basin, in particular, it's critical. So that's the main mechanism, because in that case, I think we talk about several many millimeter per year of subsidence, and that's mostly caused by the fact that the land is subsiding, and that cause is anthropogenic. It's because of water pumping, for the most part, as far as I know. That means that if you're standing on the coastline of North Java, you will see the relative sea level change at a super fast rate because of none of the processes that I've been talking about. It's not because of geodynamics, but because of anthropogenic effects that is causing subsidence of the basin. So, but among the geodynamic processes that I mentioned, of course, it's as anywhere on Earth, geodynamics, like processes like tectonostatism or genesis or operate on very long time scales. So it has almost no effect at present day. It only operates on long time scale, so it's a slow process. So we don't see it on the present day relative sea level change. So if we are talking about the short time, the quick time scales, then the post-glacial ribbon has an effect in Indonesia, but because it's I say that post-glacial ribbon operates even at large distances from the polar caps, but Indonesia is kind of far, really far from polar caps, so the effect is quite small. So the main impact is the present day thermal expansion of the ocean, but this is probably 3 times smaller than the anthropogenic effects. Now this is critical for many places in Indonesia. And your second question is which country is more affected by sea level rise at present day? We often mention small islands, like there's a COP26 in Glasgow at present day. They are discussing the vulnerability of some countries to climate change, and in many cases the vulnerability is related to sea level rise. So there was a beautiful talk by the leader of the Bahamas yesterday, and she's pointing to the fact that the islands, many islands in the oceans will be flooded because of sea level rise. That's true for some islands like I don't know, like Maldives or like the Kiribati or the Bahamas can be totally flooded and disappear, partly disappear in the next future. Now, larger countries, Bangladesh is really exposed to sea level rise, and Indonesia is well placed in among the list of the most vulnerable countries to sea level rise because it's so flat. Because Java and some parts of Kalimantan and Sumatra are so flat that any sea level rise, a small amount of sea level rise, 1 meter of sea level rise in the north coast of Java is going to cover crazy expanses of land. So that makes Indonesia very vulnerable to sea level rise. So I think that Indonesia is high on the list of exposed countries to sea level rise.
Okay, thank you, Laurent. Nabila, does that answer your question?
Okay, thanks to Dr. Laurent for the answer. Actually, I'm interested to compare the past sea level rise and the present sea level rise in Indonesia. So your answer will help me a lot to study more about this sea level rise, especially in Indonesia. So thank you very much to Dr. Laurent and also to Pak Tubagus.
Okay.
Okay. Well, if I may, if anyone has some wants to has some questions, don't hesitate to email me or and I will be happy to answer as good as I can if I can be of any help. And again, as I said earlier, I hope to visit Bandung in March with Sonia Ribowo, and to visit Rima and Ibu Yuda and Pak Tubagus. So if I would be happy to meet with any of the students who have questions as well. So we can certainly plan something like this if you think this is interesting.
Okay, thank you, Laurent. Your answer is very clear, I think. So any other questions, please? Okay, there is a direct message to me from Arif. Arif, would you like to deliver your question directly to Laurent, or you prefer me read your question? Arif? Ah, okay, he's still on the way. Okay, Laurent, I would like to read Arif questions. Can you explain more about global tide model such as FES, FES to 2014 and the DTU10? The DTU10. Did you get the question? It's about the global tide model.
The tides model. I don't know. I don't know about tides. I didn't talk about tides, and I don't know much about tides. So I'm not the right person to discuss this. Unfortunately, I'm sorry about this.
Okay. So that's the answer, Arif. So Laurent.
Sorry about this.
Okay. Didn't know much about the tidal model. Okay, tide model. Okay. So any other question, please? We still have like 10 to 15 minutes. Or probably Bu Rima, would you like to comment? Or there is something that you want to...
Itu Nadira nanya lagi ya Pak? Nadira nanya lagi.
Okay. Yes. Okay, yeah, and Nadira. Okay, so the question from Nadira, Laurent, please, Nadira. Yeah.
Mr. Husson, can you please go back to the slide about instantaneous timescale thermal effect?
Sure. How am I going to do this?
It contains about a plot sea level change in Indonesia.
The instantaneous thermal effect.
This one?
This is what I mean. So my question is, why is the sea level change in Indonesia is more fluctuates compared to the globally?
There's actually I must confess that I've been too quick in reading this publication, but generally speaking, in order to get a curve like this one, it's what Annie Kaznar has been doing is that she considered many different locations, and on average they average to this curve. So the trend is an average, but it can be very noisy in some places. So this is from the curve in Indonesia. Those are all spatial altimetry measurements. And there's I think we see an annual cycle, like this is annual cycle, for instance. The high frequency is annual cycle. And then you have, on top of that, you seem to have this kind of wavelength that has a longer wavelength, multi-decadal wavelengths. So it's often the case that you get this kind of noise if you take separate locations, and if you take all of them in the world, you end up with a more linear curve. But here you see the highest frequency that you see is the annual cycle, and then you can probably imagine some reasons why there could be an annual response. Typically, the thermal expansion of the sea level follows has an annual contribution. During summertime, it gets warmer, and it has some warmer and cooler periods. If you have and the reason why it gets so bumpy, for instance, we have El Nino. El Nino will probably peak at different locations. So it was 1998 a big El Nino, for instance. that could cause this peak here. So we have it's because the climate is not uniformly changing, and we have peaks so we have oceanic processes that have annual to multi-annual responses. That are not uniform in the world. So so we know that in some periods of El Nino, the temperature of the ocean might get really high in the warm pool in Indonesia, for instance. So that's going to cause peaks. So that explains some of the noise that you see in that curve. But all regions of the world are noisy. But if you sum them all up, the noise will mostly cancel, and you end up with a more uniform curve. I hope I answered the question.
Yeah. Okay. Nadira, does that answer your question?
Yeah, it's answered my question. Thanks a lot, Mr. Husson.
Yeah, because the El Nino, the El Nino, IOD, and ENSO also influence the fluctuation up and down the sea level. Okay. Any other question, please? If not, Laurent, I would like to discuss something with you. So as you said that the coastal flooding in Indonesia, especially in the north coast of Java, like in Jakarta, and some other megacities in Indonesia, like in Semarang, also in Surabaya.
Yeah.
So you said that the sinking megacities, or the sea level rise, or the sinking megacities is caused by the combination of the long-term oceanographic behavior, such as tidal wave, extreme wave, and also sea level rise, but also anthropogenic land subsidence. You said that I note this. That you said that the sea level rise, the anthropogenic, like water pumping and the hydrocarbon pumping is the main cause of the land subsidence in the north coast of Java, especially in Jakarta, in the coastal megacities like Jakarta. But I found that in fact not only coastal megacities that have high rates, subsidence rates. So in Jakarta, in Semarang, okay, it's because of the water pumping, as you said, or hydrocarbon pumping. But in aquaculture area with no settlement over there, also experiencing high subsidence up to 10 centimeter per year. So what is the main cause of this land subsidence? Because I believe over there is no many water pumping, because the settlements are very rare, and also there is no hydrocarbon pumping also, but still the subsidence rate is high. So what is the main cause of that? If you said that the land subsidence is the main driver of the land subsidence is caused by the anthropogenic factor.
Well, you know this better than I do. Maybe you could answer this question. So I don't know about the special variabilities that you mentioned. My first guess is that there's also an effect of sediment compaction that of course all the north of Java is covered by young sediments, and those sediments there's compaction, so the thickness of the layers decreases because of compaction. So that might be a reason why. And then if there's no there's no water pumping, no hydrocarbon pumping, if there's no pumping in nearby, nearby being I don't know, less than several tens of kilometers away from the place, because aquifers are really wide. So if you're pumping, in at a given place, if you're pumping here, then you might expect the aquifer to be impacted even remotely. So that's we're talking about large aquifers. So that might be an effect. Otherwise, besides, if you know that there's no effect of water pumping or hydrocarbon pumping, then I don't know. The only candidate for such rates would be I don't know. Sediment compaction would help, that's for sure. But I don't expect such rates. I don't expect 10 millimeters per year with sediment compaction. So I don't know. Do you have ideas about this, Tubagus?
Yes, but that's why I asked you, because I'm not really sure about my hypothesis, Laurent. Yeah, because it's happened in some aquaculture areas with very rare settlements and no hydrocarbon pumping effect. But still, the subsidence rate is high. So, or even in the deltaic environment, which the sediment, the sediment transport is very high over there, but still the land subsidence also high. So, yeah, it's maybe if you come to Indonesia, and then I will show you some areas that experiencing high subsidence rates, but over there is no very rare. I mean, the settlement is not very dense, and also there is no hydrocarbon pumping. So yeah, but the subsidence is high. Probably your question about the sediment compaction is true. It's true, but probably also the sediment transports is reduced time by time. So the sediment cannot compensate the sediment compaction. Sediment transport from the land couldn't compensate the sediment compaction in the coastal area. So the subsidence rate is high. Probably, I don't know.
Yes, I think that's something that has been observed in. Now that you mention it, I think this is a very good point. The fact that there's no more, because all the rivers are being channelized. Yeah. There's no more sediment deposition. Yeah. All the fresh sediments are being instantaneously washed out to the sea. They no longer have time to settle in the coastal plains. I think that's a really good point. Yeah.
Yeah, because there are so many river works, like dam construction, and also change of the river mount. So it's also reduce the sediment transport to the coastal area, and then the sediment cannot compensate the sediment compaction in the coastal area. So that's why probably, I don't know. Okay.
No, I think that's a very likely explanation, Tubagus, that you have here.
Okay. Any more question? I think the time is up, Laurent. Okay. Ladies and gentlemen, finally we come to the end part of our lecture. So we would like to say again to Laurent, to presenter, for your good presentation, for your informative and interesting topic today. And to all audience, thank you for your active participation. Hopefully, this lecture will be beneficial for all of us. Thank you, and I'll give it back to Salsa. Thank you from me. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Tubagus. Thank you, Dr. Laurent, for the presentation. It really gives a new insight for us and also the interesting discussion we had earlier before. And thank you for Mr. Tubagus, who led the discussion session very well. And I hope all the participants get some new knowledge, especially about geodynamic and sea level. Thank you for the participants to join our student course in this 4th series. Just to remind you that we will have the last series of student course in this semester with very interesting topic. For further information about the next student course, you can check to our Instagram at oceanography.itb. So see you in the next student course. Thank you again, Dr. Laurent, Mr. Tarya, Dr. Tubagus, and all the participants. Stay safe and be healthy. Wassalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Laurent.
Thank you,
Thank
Laurent.
you.
Thank you.
Bye-bye.
Budina.
Have a good weekend.
Au
Thank you, Pak
revoir.
Tubagus.
Okay,
Yeah.
thank you. Okay, bye.
I'll keep you updated about the report, Laurent, hopefully in this weekend.
Ah, yeah. Thanks, Riva. And again,
Okay.
to all students, I would be happy to keep the discussion. So don't hesitate to email me. Yeah?
Okay. Thank you. Bye-bye.
Okay.
Bye-bye.
Looking forward to seeing you in Indonesia, Laurent. In
Yes.
March, right? Okay. Thank you. Bye.